Taking a look at dichotomous outcomes over time. So we're considering time as one of our variables in this case. So this extends logistic regression into considering the risk of some dichotomous event, so just like logistic regression, but we have to consider also the time that has elapsed. So there's two dependent variables that we're looking at here. And what we're considering here, importantly, is that our experiments don't go on forever. And sometimes people drop out. And so we might lose subjects to follow-up. We might also just simply have to call our experiment before all of the subjects have experienced the dichotomous event. Now, in many cases, what we're looking at for this dichotomous event would be death. And that's why this is appropriately named survival analysis. We're looking to see whether the risk of not surviving differs between two groups or across some continuous variable or something like that. As far as our independent variable goes, or our predictors, we can have anything we want here. So it's very similar to logistic regression, but now we have an additional time variable that we'll consider. And so it's not called logistic regression because it's actually quite different. It's called Cox regression in this case. So let's get into it. Let's go to our data for this week. So here we're looking at a few different variables. Of course, we have one for time. And here we're looking at, I know it says survival time. This is a general term. This just means time until the event that's over here in status. Okay, so we're looking at the number of days for each subject. 306 for here, 455, 1010, you get the idea. And then we have our dichotomous event. That would be status. Now in this case, they are either dead, that'd be a 1, so that's the outcome we're interested in and we'd like to avoid it. And 0, you'll note, is marked censored. Obviously, if we carried this experiment out forever, all of our subjects would have the status of 1. They'd all be dead, because that's just an inevitable fact of life. Everyone will die at some point. What we put with 0 is that they are not dead yet. And it could be for a couple of reasons. It could be that we ended our experiment, like I said. Maybe we just didn't hear from them ever again. They were lost to follow-up. The last time we saw them, 1,010 days into our experiment here, they were still alive. We couldn't get a hold of them since, so we don't really know what happened after the 1,010th day. So that's our last follow-up with them. So we use the term censored here, just meaning that the outcome hasn't happened yet. And Cox regression will take that into account. All right, so I have my two dependent variables here, time to the event and what event happened, either death or no death yet. Then I've got some things that I might care about here. Age, of course, age matters. So here's the age in years of each of the subject. What we're looking at here is the risk of death in folks with lung cancer. And so a couple other things we're going to consider here. Sex, in this case 0 is male, 1 is female. And then we have our, we'll get over here, this ECOG performance score. And this ranges from 0 to 5. If you care to Google it, you'll find something very similar to this, I would imagine. So ECOG being the Eastern Cooperative Oncology Group. I read that right as I said it. And they have this grading scale here from 0 to 5. 0 is good, and 5 is really bad. Okay, so this would be an obvious confound if we had a bunch of 5s in here. Hopefully that's not the case. So let's just do a quick check here. We could do this in SPSS. I think it's just a little bit faster actually to do it here. Okay, so we get our 0s, 1s, 2s, a couple of 3s. I don't see any 4s or 5s. Okay, cool. So we're good to go. All right, so I'm just going to highlight all of these data here, copy them to my clipboard, and we'll head on into SPSS. We'll paste in our data. There it is there. Notice we have some missing data. This happens. This happens when you're working with data sets sometimes. No worries. What we're going to do now is analyze. And in this case, we're not going to where we have before. It won't be our binary logistic. No, no, no. Even though this is regression, SPSS puts it over here in this survival tab. So we'll go survival and then Cox regression. All right, from here, we just simply need to put in our variables of interest. So time is time. That makes sense. Status is status. Cool. Now I need to define the event, because this might be other things. We might have a range of values and we want to set a cutoff or something like that. In this case, it's very simple. 1 means the event has occurred. In this case, death. Okay, so we're all good there. And now I just need to put in my covariates. In this case, let's say that I'm most interested in whether or not men and women have different survival times with lung cancer. So we'll put sex in here. Now, of course, I realize that age and their functional status, this ECOG here, probably also matter. So we'll want to take that into account. So I'm going to build another model by clicking Next. And here I'll just take all of these variables and add them. So now you can see I'm going to run 2 models, my unadjusted hazard ratio for sex, and I'll get my adjusted hazard ratio for sex after controlling age and our functional status on the ECOG in my second model. Okay, just a couple of things that we need to do here. I can define the which variable I want to treat as categorical here. So in this case, it'll be sex. Now I realize it's 0 and 1, but let's make it categorical. We'll put that in there. And what that's going to allow me to do is generate this really nice survival plot. And it only works with categorical variables. Let's say I wanted to put age in. Not going to happen. Notice SPSS will not let you do that. Sex, it will let me because I said this is categorical. So it'll plot one for the zeros, that's the males, and another line for the ones, the females. So we'll say, okay, save. We're not too worried about saving any of this. This might be helpful to some folks, not for us. We do want the confidence interval for my exponentiated regression coefficient. Now, just like last week, the exponentiated regression coefficient is what I'm after here. So we're not getting the odds ratio, instead we're getting the hazard ratio, which is kind of similar to odds ratio and relative risk, but it takes time into account. So we're looking at risk of an event over time. That's about it. We could tell it to do some bootstrapping, but we're not going to worry about that. That'll just take a lot more time. And we'll say OK. And we get our output over here. Let's see if we can make sense of this thing. Okay, so as usual, we're going to start with a block. We don't really care about this. This is just nothing here. Okay, block 1, we're seeing the unadjusted hazard ratio for sex. In this case, the effect of 1 being female here. So the risk of females is what we're looking at. Right? We want to always know what our 1s and 0s mean. And this regression coefficient tells you the effect of 1. That is being female. And notice it's negative here. When we exponentiate it, we get this value less than 1. So about 0.59. So that means that females in any given period of time have only about 59% of the risk of males as dying from lung cancer. Of course, we get a confidence interval over here, and we should always take a look at that. What we're looking for here is 1, because this is a hazard ratio, and any number divided by itself is 1. Notice we don't find 1 here. So the risk is somewhere between about 43% and about 82% in females compared to males. So males are more likely to die. And this is true across a range of conditions. So that's good. This is not surprising. Okay, let's take a look over here. And now we're going to take multiple variables into account. We've got our ECOG status, right? This makes absolute sense. The higher you are on that ECOG, the more likely you are to die. We saw that in the scale itself. Let's take a look. We go back here. Hey, the higher you go on here, the more likely you are to die. Okay, cool. So that makes sense. Again, this isn't something we care about. Again, we're just using regression here to control for this functional difference that might exist between men and women. We also want to control for the differences in age. And this might sound surprising. What we're going to say here is that age does not increase your risk of dying. Now, I know if we live long enough, we will eventually die. Age is always a risk factor for death. But in this group of folks with lung cancer, we didn't see age as being a strong predictor of death after we controlled for functional status, which is likely related to age as well as severity of the cancer, and sex. So yes, age still matters. No one's going to live forever. That's not what this is saying, even though we have one in this confidence interval. It's just saying that age was not a significant predictor after taking a couple of other variables into account. Okay, and then finally we get our effect of sex, in particular female sex. Again, we're less than 1, but hey, things actually look maybe a little bit better, right? We went from that like 0.59 hazard ratio to about 0.58. Yeah, not much better, but this is a good thing, right? This is just telling us that those other variables weren't really different between my sexes. There wasn't a big imbalance of age or functional status, and so we didn't get this massive shift in our hazard ratio. So it's great when the adjusted hazard ratio matches the unadjusted. This tells us there's probably nothing fishy going on with our data there. Nothing really to worry about in terms of imbalanced confounds. Again, we look at the confidence interval. You can look at the p-value if you really want to. But there's no 1 in this confidence interval, and so therefore sex is again a significant predictor of death in folks with lung cancer, with women having about 58% the risk of dying over any period of time compared to men. Could be as high as 80%, could be as low as about 42%. Then what we get is this curve we don't really care about. Let's go all the way to the bottom. Great. This is our nice survival curve, and this shows us pretty clearly that females here, that'd be the 1, tended to survive longer than males. That'd be the 0 here. We could go in here and clean this up. I'm not going to worry about it here. But hopefully what we see visually matches what we're seeing in our table up here. And indeed it does. So the risk of dying in any particular instance of time is about half that in females than males. And that about does it for Cox regression. If anything on here is unclear, make sure you use the questions box so I can address your comments. I'll see you next week.